Then we computed what would be the pattern you would get if you were to shine a beam of X-rays or electrons through a material which had that property. And what we showed is that the pattern would be patterns of sharp spots, a kind of snowflake pattern with points between points between points, like shown there, and reflecting the symmetry of it's full of pentagons as you study the pattern. And just as we were getting to this point in our results, someone came to visit me and Dove, that was David, bringing a paper, a very interesting paper, by a group working a few hundred miles to the south of us, led by Dan Schechtman, Ilan Blech, Denis Gratius, and John Kahn, in which they had, knowing nothing about our work, accidentally made a material which, when they shone electrons through it, produced a pattern that was virtually the same as the one on the left. And we didn't know anything about them. They didn't know anything about us. These were two parallel developments that happened to coincide at the same time, and which were mutually discovered thanks to David's bringing the paper to me at a particular instant that we can all remember. That was the beginning of the story of quasicrystals, when it first became apparent that quasicrystals are possible. So, over the next few years, many examples of quasicrystals began to be discovered using different combinations of elements and using different techniques for synthesizing these materials in the laboratory. But there was a question that was bothering me from the beginning. Once we knew we could make them in the laboratory, why is it that they were never found in nature? In nature, we find crystals. We don't just synthesize them in the laboratory. We also can make them in nature. Why hadn't we seen quasicrystals? Or maybe there were quasicrystals and we just hadn't noticed them, because until this moment, no one had the idea that they might exist. Maybe we've been walking across them every single day and just simply hadn't noticed them. Or maybe it's impossible. Maybe there's some reason why it can't be made in nature, because in the laboratory we can put together groups of atoms of different types under highly controlled conditions. Maybe there's something about quasicrystals that demand that. And that was an idea that some people had been proposing at the time. But because of the model that I passed around, because it suggests that in principle there should exist the possibility of groups of kinds of atoms or groups of atoms or combinations of atoms and molecules that would be forced to make this structure, it seemed logical or possible that they maybe should exist in nature. We just have to look for them. The first attempts to look for them didn't come out all that well. But beginning in the 1999, working with Peter Liu and others at Princeton, a systematic search began, which proceeded for a few years, using a number of techniques I don't have time to describe here tonight, but the bottom line is they led to failure. And the failure continued for year after year after year until 2007, when we were contacted by this fellow, a fellow I'd never heard of before, Luca Bindi, who was a mineralogist working in Florence at a small museum at the university there. And he offered to come and work with us and to explore whatever we wanted to explore in his museum. When he said, but there's, in my basement of my museum here, there's these drawers, this collection of these little boxes, each of which has a little piece of little mineral inside it. And one of these minerals in this set of drawers, which numbers some 2,000 or so, is this one. I've blown it up here. It's called Katirkite. It's supposed to be a crystal mixture of copper and aluminum. So it's not a quasicrystal. It's supposed to be a crystal. It's supposed to be the darker material here. However, I know that aluminum and copper are elements that have been seen in the laboratory as some of the elements that are included in some quasicrystals. So maybe that's a good reason to check out this particular candidate. After all, this is not a nugget of one substance. It's a rock which contains a conglomeration of different minerals, and maybe one of them turns out to be a quasicrystal. Maybe most of it's this crystal of aluminum and copper, but maybe something is something else. So So he sliced and diced the material, sent some tiny little grains of it to Princeton, and on New Year's 2009, at around 5 in the morning, I gathered there with our electron microscopist, Nan Yao. We put some of those grains under the electron microscope, and within a matter of instants, popped up a beautiful pattern of spots, just like the one I had shown in the previous slides, just like the one that Shechtman had seen, but much better, much finer, truly point spots, truly perfect, much more perfect, or as perfect as anything I had ever seen made in the laboratory. So that should have been the end of the story. We should have declared victory. We won. We found the natural quasicrystal. It's in there inside that rock. But it wasn't, not by a long shot, because curiosity took the better of us. In particular, I was interested in the question of how is it that nature managed to make this very perfect quasicrystal in this very messy rock situation, when in the laboratory we need to only form these quasicrystals under very controlled conditions? What does nature know that we don't? Or what does this tell us something about nature? So that led me to talk to geologists, both at Princeton, at the Smithsonian in Washington, and elsewhere, to try to answer that question. And their response was universally the same. They would say, okay, thanks for telling us this story. I can now tell you, given the information that you've provided, that what you've got there is impossible. Not impossible because it's a quasicrystal, but because of the chemistry of the quasicrystal that you claim to have discovered. You're claiming to have discovered a quasicrystal composed of aluminum, copper, in this case, some iron. Now, iron is plentiful in nature. Metallic aluminum, alloy of aluminum, doesn't exist in nature. It's impossible. Aluminum is plentiful on the earth. There's lots of it. But aluminum has a tremendous affinity for oxygen. So whenever you find aluminum, it's always going to be attached to oxygen. And you're telling me that isn't what you found. The only way we can make aluminum separate from oxygen is in an aluminum foundry, in which case what you've probably got there is, well, a 4-letter word, a piece of slag, a piece of industrial byproducts. Maybe it was made someplace in downtown Berlin or near some aluminum foundry someplace. But it's certainly not something natural. And they sent us away, imagining that they would never hear from us again. What they underestimated was the stupid stubbornness of Luca and me, because we weren't about to give up just based on that claim. The argument seemed that it was impossible seemed to be of the second kind, something that wasn't certainly, that was based on common assumptions about the way aluminum forms, but not absolutely proven in the way that you would prove 1 + 1 = 2 or something like that. So that led us to explore further, see what we could learn about the sample. Where had it come from? And now, I should also tell you that in the field, you cannot tell what you are digging, what you are collecting. You can't tell by looking at a rock or looking at a grain whether it's a quasicrystal or not. It doesn't come out beautifully faceted the way you might form it in the laboratory. It's been out there in nature for a long time. So all you can do is collect as much material as you can, panning it as much as you'd like to pan for gold, so you can at least capture the higher density material that is the material that most likely would be quasicrystalline, but so are lots of other things. Gather as much as you can, bags and bags and bags of it, about 1.5 tons dug and about many pounds of material that you bring back, and bring it back and then begin to look through it grain by grain. Millions of grains, grain by grain. So it takes weeks before you begin to make much headway in the search. It took about 6 weeks before we got a first result, a first reading from Luca, who was doing this grain by grain study. He presented this particular grain. It was one of the grains he had noticed in the field that he thought might be promising. And it turned out that it really is. The darkish material there is characteristic of what the material we had seen in Florence. And in fact, is characteristic, both of them were characteristic of a certain kind of meteorite. And when he viewed the sample, he noticed it had some of these shiny material on it. And when he extracted that shiny material and shone electrons through it, or I'm sorry, X-rays through it, he found, sure enough, a beautiful pattern, beautiful tenfold pattern, just like you would expect to have for a quasicrystal. In fact, it had the exact same chemistry as the quasicrystal that we had discovered in the sample in Florence. So it was at that moment, really at that moment for the first time, that we were really sure that quasicrystals really existed in nature. We had picked this sample out of the ground ourselves, and that crazy detective story that we had worked out was really true. It wasn't just we had made some mistake along the way. So that was really a key moment in the whole story, when impossible seemed to really be possible. And that's really just the beginning. We discovered in going through these millions of grains, now 9 different grains, each of which tell us about different parts of the story about how this sample formed, including a slew of never before seen crystal minerals, not just quasicrystals. So by this time we found 3 different types of quasicrystals, plus lots and lots of a number of new crystal minerals, one of which is this one over here. It's a personal favorite. The team, behind my back, put together a proposal to name this mineral Steinhardtite. So I'm very proud of this, this mineral because it means I have been mineralized permanently as a result of this work. Even though it's not a quasicrystal, it's a crystal. Its discovery led us to discover a new type of crystal besides the original. And we also confirmed something that seemed to be, first arose when we began looking at the Florence sample. As we began to study the Florence sample and then the later samples we recovered in Chukotka, we confirmed that our sample was not made on Earth. It was natural, but it was not made on Earth. It was made in space. It was a piece of a meteorite. And not just any old meteorite, but a special brand of meteorite, which meteorite experts call CV3 carbonaceous chondrites. And what's important about CV3 carbonaceous chondrites, what makes them the most popular meteorites to study among meteorite experts, is they are the oldest meteorites to have formed in the solar system. They formed before the planets formed. They are the primal material from which planets were eventually created. And so if you want to learn something about the origin of the solar system, you want to know something about these chondrites. And what we've discovered now is something that no one had ever seen before, that among the minerals you can find in carbonaceous chondrites in this primal material are quasicrystals. And these quasicrystals really do have this peculiar chemistry that geologists and meteorite experts had at first told us were impossible. Now we know they are possible. They are actually part of the fabric of the initial material that makes up our solar system. Perhaps playing some, and perhaps the processes that created them that we still don't understand are actually important processes that will give us new clues about how the planets formed. That is not the end of the story, not by a long shot. That's in fact a long shot being taken over there. That's Paul Asamoah at Caltech about to fire off a cannon, in which one of the things we could do is we could do experiments that would actually fire together material that would collide in much the way the meteorites might have collided and see if we could make a quasicrystal that way. And sure enough, we did. The thing on the images on the right are images of an asteroid in the asteroid belt that, using information gained from our experience with these cannon experiments and also measurements of the isotopic ratios, ratios of isotopes in our quasicrystal, in our quasicrystal sample, and other reflectivity information and the like. This is a candidate for, might be the parent asteroid which from which our quasicrystal originally came. So that we can imagine someday not looking in Chukotka, but going into space and maybe visiting an asteroid like this and discovering the quasicrystals there. And that might sound impossible, but there are people, including people here at Harvard, that are very interested in the possibility of asteroid mining and visiting asteroids. And some of that, you may know, has already taken place. So although it might sound impossible, it's probably impossible of the second kind. And maybe someday will find quasicrystals at their point of natural origin, and that'll be the key to figuring out the full story of them.